Okay, why don't we go ahead and get started? It's 5 after. We have a nice contingent of people. I have two groups that are going to be presenting tonight, so I will do the intro for the first one now. We have a group who is working on sentiment analysis of the conflict in Ukraine to see if the political leanings of a person affects their sentiment either for or against the war. So I'm going to give the mic over to Pareekshith Krishna and let him explain to you what the story is on this.
Cool. Thanks, Dr. McMahan. Let me just share my screen first, then we can get started. Okay, can everyone see my screen now?
Yeah.
Cool. Siddh and UA, are you guys ready?
Yeah.
UA, are you there? Okay, cool. In that case, let's get started. Cool. Good evening, everyone. We are the Big Data Group, and today we're going to be discussing our spring project, which is identifying the association of political affiliation and sentiment on the Russia-Ukraine conflict.
Regarding the Russia-Ukraine conflict, in February 2022, Russia invaded Ukraine, and while this action was internationally condemned, in Twitter there were a variety of responses. For example, we have a tweet here supporting Ukraine, while another support is against Ukraine and supports Russia. And this was the basis for our project, as we wanted to analyze how political affiliation affected the varying sentiments on the Ukraine conflict. And for the dataset that we use, it was updated daily, and it contains over 10,000 tweets by different Twitter users related to the conflict. And there are 36 unique details about every single tweet. And while we only use the text for our analysis on the tweet, we are planning to use other unique values for the tweet in order to increase the accuracy of our models in the future.
And for the methods of sentiment analysis, there are usually two approaches to sentiment analysis. One is machine learning, which labels the text as positive or negative during the training process and transforms the text into numerical feature vectors. And then a classifier will be trained to classify the text as positive or negative. The other approach is called lexicon approach, which is used in this research. And it involves creating a lexicon with words matched to labels such as positive and negative, or matched to a value representing the intensity and the polarity of the text. During the classification process, a sentence is tokenized to match available words in the lexicon. Finally, a combining function such as sum or average is used to find out the final sentiment. The first step to the lexicon-based method is preparing the lexicon. And in this research, we combine two lexicons together. The first one is Weather Sentiment Lexicon. The second one is NRC hashtag sentiment lexicons. And NRC stands for National Research Council of Canada. The second lexicon was automatically generated from tweets that contain sentimental seed words, which means basic words such as rich, good, bad, that you can easily infer the sentiments of. And it not only contains words, but also contains phrases. The sentiment value of each word is associated with numbers of appearances in positive or negative tweets. And during the combination process, we first delete the punctuations in the entries of the two lexicons. And then we need to delete unnecessary entries, such as entries that contain determiners. And we know that determiners are inherently neutral. And then we need to scale down the sentiment score of both lexicons to fit in the range of -1 to 1 for consistency purposes. And sometimes one word is present in both lexicons. In this case, we have to only keep one entry in the final combined lexicon. And we decided to keep the entry with the most intense sentiment, which has the highest absolute value. We are basing our work of the weighted sentiment model, whose algorithm is shown as follows. It matches a single word to it. So first, it parses a sentence into different tokens, which basically means different individual words, and it then matches single words to its sentiment score in the lexicon, and the word should be labeled as neutral if it's not found in the lexicon. And then the model performs negation checks, spot checks, and list checks on each word, which all serve similar purposes, which negates the sentiment score of the word depending on varying circumstances. It also contains a booster dictionary, which contains a list of words that can that multiply the sentiment score of the next word, and examples of the booster words are considerable, amazing. And the final output is a list of scaled negative, positive, and neutral values, which add to 1. During the building of our model, we improved the matching algorithm of the original weighted sentiment package. We used lemmatization with spaCy, and the lemma stands for the root of the word. For example, the lemma of the word match is match. First, we check if the word or its lemma and the next word or its lemma is in the combined sentiment lexicon. So the combined sentiment lexicon contains word or phrases that are made up of 2 words, not 3 words. If the phrase is in the lexicon, we set the sentiment score of each word to be the sentiment score of the entire phrase and store them in a list. And we skip the series of checks on the second word of the phrase since we treat the phrase as a whole. Finally, we added more rules to weighted sentiment package. In this case, in this circumstance, we consider 3 cases. The first case is when we encounter opening and delayed adjective and adverb, which modifies the entire sentence. We need to make sure that the sentiments of the adjectives or adverbs and the sentences they modify have the same sentiment, or in another word, they have the same sign of sentiment score. And the second case is when we encounter word phrases and non-phrases, and we need to negate the word phrases, the sentiment score of word phrases and non-phrases, unless both of them have positive sentiment score. And I will show you why we need to do this. For example, there is a sentence, I stopped the villain. In this case, both stop and villain would have negative sentiment score, but the overall sentiment score of the sentence is apparently positive. So we need to negate that. And the last case is when we encounter special transitional expressions, which means transitional expressions that contrast or shows an exception. And these are an example of the expression would be but. And we need to lighten or dampen the following or preceding sentences if we encounter this case. And here is an evaluation of the accuracy of the models. In this case, we use the Twitter's US airline sentiment dataset. For the original wager sentiment model, we achieved 32.02 accuracy. And for the modified model, we achieved 59.32% accuracy.
So now we're going to discuss how the political affiliation of a Twitter user was determined from just their tweet. To do this, we utilize the logistic regression model, which is a machine learning classification algorithm that is pretty much the go-to for all binary classification problems, which in other words means problems with only two possibilities, like true or false. In our case, the two choices are conservative leaning or Republican and liberal leaning or Democratic. And the model determines the probability of the tweet being either. If the percentage is greater than 50%, then it's more Democratic and we just consider it as a Democratic tweet. But if it's less than 50%, then we consider it as a Republican tweet. To create the model, a Kaggle dataset was used, which contains over 80,000 tweets written by Congress politicians, along with their Twitter handle and their political affiliation. The number of tweets by Republicans and Democrats are roughly the same, which is good news because it means that the data is well enough balanced to use directly. So what we first did was we converted the Republican and Democratic names in the political party category to zeros and ones respectively so that we could use it in the logistic regression model. And then we converted the text of the tweet into numerical values because Python can't understand text. And we did this by using count vectorizer, which removes punctuation marks, separates the sentence into words through a process called tokenization, and then assigns each word a unique value, and then counts how many times that value or that word appears in the text. And after doing all of this, we use scikit's logistic regression model and fit the data using an 80% train and 20% split. Doing all of this, we obtained a 80% accuracy, which is definitely good, but can still be improved upon in the future by adding additional features. We then fed the data from our original data set with the tweets about the Russia-Ukraine conflict in the model and got our predictions. And so the results, as can be seen here, clearly indicate that regardless of your political affiliation, a majority of the tweets had a negative sentiment, whereas there was a lot less neutral tweets and even less positive tweets. And we decided to look at how this the sentiment changed over time. And as can be seen in these graphs, not much, right? The sentiment did not change over time, and the ratio stayed roughly the same throughout, which can show that the political affiliation probably doesn't have too much of an impact on a person's sentiment about this conflict.
So we did some statistical analysis on this data, and we conducted a chi-square test for association in order to determine if there's an association between political affiliation and sentiment on Ukraine. And from the chi-square test, we received a chi-square value of 5.8037, a p-value of 0.0549, and degrees of freedom of 2. While the p-value is the p-value is greater than 0.05, so we didn't necessarily get convincing evidence for an association between political affiliation and sentiment on Ukraine. This might change as we get significantly more accurate models, which can potentially change the p-value if we recalculate the values with more accurate predicted values.
So now we're going to go over some of the sources of error. And the first one of them is the fact that it's pretty difficult to ascertain the political affiliation of a tweet from a politically neutral tweet, such as "I stand with Ukraine." Currently, our model identifies tweets like these as democratic, but in the future, we obviously want to go further into depth and see if the Twitter user has any past tweets that could reflect their actual political affiliation. And another major issue is sarcasm, which our models currently can't detect. While the number of sarcastic tweets is probably lower than the number of honest ones, it still could constitute a significant amount of the total number of tweets, which is something that we definitely need to look at.
Some areas of future research are making the political affiliation model more accurate by utilizing Twitter API and by adding other features, such as following lists, in order to increase the accuracy of our political affiliation determination, and also experimenting with other machine learning classification models in order to get more accurate models, and matching changes in sentiment with key events in the conflict. For future research in our sentiment analysis is reducing the dependency on spaCy for sentiment analysis of short text and developing faster algorithms for sentiment analysis of short text.
We would like to thank Dr. McMahan for being an excellent mentor and advisor and for always giving us suggestions and ideas and tips to help us in this project. We would also like to thank our research group members who aided us and made this possible. And finally, we would of course like to thank ASDRP and the Computer Science and Engineering Department. Thank you very much. Any questions?
Okay, questions. If you can either unmute and ask your question, or you can type your question in the chat window. And since we must have a question, I think I'm going to call on somebody. Rob, you can be the first questioner.
I knew you were going to do that, you dirty dog, you.
Just because I've been rolling in the mud, you don't have to point it out.
All right. Did you check for, or did you give any thought to potentially adding or injecting bias into your algorithm by choosing to make I guess the total scores for Democrat affiliation more positive and the total scores for Republican affiliation negative?
I think it's possible. We definitely have to take a closer look into our data sets and see if we can get a more random sampling, because it's possible that the data set that we got it from might have had some political inclination. So we might take a look into that and see if we could get more random sampling, possibly by using the Twitter API to get current recent tweets by different political figures in the current landscape. So that's something that we will take into consideration.
Good answer. Great answer.
So here is a question from the chat window. Do you have any plans for further examine the situation with more refined political spectrum, like more detailed than simply left or right?
Yeah, that so yes, that's something that we want to look at as well, because yeah, obviously it's not just Republican or Democrat. There's also independents and people who, you know, don't really see themselves as one, but like are more in the middle or like in somewhere in between. So we're gonna take a look at that as well. Currently, our idea for that is maybe to look at different data sets that might contain other values for independence and other maybe more specific parties, rather than just like Republican or Democrat, maybe saying the extent to which you are Republican or Democrat, So for example, Bernie Sanders could be considered like a socialist, is what people say, right? So maybe like, are you going to the extreme or are you more moderate? So that's something that we might take into consideration in the future.
Okay, another thing that I seem to remember you saying on one of our earlier meetings that I didn't see here was there seemed to be a slightly higher negative sentiment among liberal Democrats
Right.
than across the rest of the spectrum.
Yes, that's true. We were considering adding that, but we felt that like the difference is like quite like pretty small. So because of that, we didn't think that the affiliation had like a true impact on that. But I think as we do further research and get better models, we might see that that difference could escalate or like change, and we might use that as further evidence to support our conclusions.
Okay, so we got a couple more from the chat window. I was wondering how you can use a binary process in relation to political leanings, which can be pretty vaguely defined. Can you explain that process a little bit?
Right. So as I just explained a few minutes ago, currently we only looked at left or right. We haven't, as part of our further research, we plan on looking at more varied spectrums. Yeah, that is one pitfall currently, which is the fact that we can only look at Republican or Democrat, and again, not to an extreme degree of certainty, because obviously one tweet itself can't like tell exactly who a person is, right? So because
and following on with that, do you have an example of what a neutral statement about the conflict would look like?
Yue, can you would you mind providing a neutral statement or an example of one?
So maybe I think I have left something behind, like during the presentation. So, a neutral, like if a sentence is classified as neutral, it will just have like higher neutral values than positive and negative values. Like it could have a neutral value of 0.4 and the other like positive and negative would be like 0.3. In this case, it will be like, for example, I think I can make one up. It's like, for example, a reporter reported that Russian army stopped like 90 kilometers out of from Ukraine. In this case, the only word that would be classified as a negative would be stops. So that would be a case of neutral statement, since it's like you are referring to someone else.
Okay, do we have any other questions from anybody in the audience? Okay, I want to thank.
Wait, I had to unmute myself. I have a statement. Oh, buck up, bucko. First, excellent job. Second, you may see some refinement of a particular sentiment being associated with a particular affiliation as you broaden your spectrum of affiliations. In other words, you get greater granularity, you're going to be able to probably see a greater delta.
Definitely. I think for now, I think in order to improve our model, we probably want to consider neutral or like more neutral statements like I stand with Ukraine, like which don't really go to any political affiliation. I think we should probably say that that's like a neutral statement for now. But then as we go and look at a Twitter user's past tweets, then we could probably make better analysis and better predictions about their affiliation, rather than just looking at that one tweet and just saying, oh, you are one. like that.
Yep. Thank you again.
Thanks.
Okay, thank you with the big data group. Okay, we have another group who is presenting for us today. Yasha, are you here? Let's see who we've got. Give me a second.
Larry, I wonder if Suresh's group wants to go first.
Oh, is Suresh doing one also?
I think so. Is that right,
Yeah,
Rob?
I am. Can you hear? Can you hear me, guys?
Yeah.
Yeah, go ahead.
Okay. Yeah. So
Yeah, why don't you go
you hear
first,
some
yeah.
background noise because I'm on my evening walk. But yeah, I'll just briefly give an introduction to the project. Right. So what the team is doing is it's like they are trying to answer the question. It's like, does demographics impact the crime rate? So they have basically selected some kind of geographical areas all over the US, and the team has collected demographic information like income, jobs, right, ethnicity, and so on. And then the team has built a model which predicts whether the area is high crime, medium crime, or a low crime. Right? So this kind of analysis is always controversial because you're using personal information, demographic information for this. So we will discuss that when we get to the results, but I'll hand over this to the team. Okay, go ahead, Amod and team.
Hello, we are the Subramaniam Lab Group, and our project is predicting crime rate in the United States. My name is Amod.
My name's Andrew.
And my name's Rashawn. So the introduction. So why is crime such a big problem? Crime negatively impacts one's life and other health outcomes. Crime also negatively affects innocent people. Additionally, there are several factors which are common to society which can increase the rate of crime. The ability to predict crime and the crime rate of a city is useful for adjusting policing, giving insight to prospective citizens of that city, and more. So what is our goal? To start, we collect data on different US cities as well as the crime rate of that city. Then we can build a machine learning model with that data and test its accuracy in predicting the crime rate for a city. Then we will be able to use our model to predict the crime rate of a city in the United States and use it for the reasons mentioned above. We'll talk more about this process in the next couple slides. So data collection. We collected data from about 200 cities. Our data collection features included crime rate, median household income, population density per square mile, education rate, and that's college degrees, and homelessness rate as a percentage, average age, percent Democrats and percent Republicans, employment rate, disabilities, police count per 10,000 people, and stress score. We got our crime rate from a website which uses crime rate from the FBI to assign a city a value from 1 to 100. Most of our data was a number or a percent. However, we had to encode the state names into a numerical value because otherwise the model wouldn't work. Most of the data was from websites including Census, Data USA, and World Population Review. In the future, we plan to add more data, including adding features and getting close to 500 cities.
To make gathering data easier, we wrote a program that web scrapes data from websites and writes it into an Excel file. It uses the following Python packages: OpenPyExcel, requests, and RE. OpenPyExcel is used to read data from the Excel file and write back into it. Requests handles getting the HTML from the website, and RE is used to find the specific part of the HTML with the value that we're looking for. So the first couple of lines in the code segment are getting the state and city name from the Excel file, and then we generate the URL of the website. Next, the website is opened up and we're able to get the HTML code from the website. The HTML is searched for the above string, and then unnecessary punctuation is stripped away to isolate the value, and then those values are written back into the Excel file. Model building. So before we could build our model, we had to prepare our data. So we used Jupyter Notebook to write our code, and Python packages such as pandas, matplotlib, NumPy, and scikit-learn to aid us in analyzing our data. The first thing we did to prepare the data was remove the column for city names because that wouldn't affect the model. The second was encoding some of our data. As Harshan said earlier, most of our data was numerical, but the state names weren't. For the model to work, we needed to encode the state names. So we experimented with two types of ways to encode the data. The label encoder transformed the strings into numbers from 0 to 49. And the picture in the top right-hand corner shows this. We also tried out one-hot encoding, which creates 50 columns for each of the state names and assigns each row a binary value depending on which state it is. So as an example, we have a screenshot in the bottom right-hand corner, and the bottom 3 rows are cities in the state of Wyoming. So the value in the Wyoming column is 1, but 0 for all the other state columns. We decided to use label encoding instead of one-hot encoding because it was a lot harder to look through our data with 50 columns. Additionally, there were some cells which we couldn't find data for, so we accounted for this by imputing data with the average value of the column. We use the random forest classifier in the scikit-learn package to form our model and use 22% of our data for training. Currently, our accuracy is 59%.
Now there's model results and interpretation. After using our model to predict the crime rates for the rest of our data, our model achieved an accuracy of 59%, and we're currently in the process of increasing that value. Due to limited time, our model has lots of factors that have yet to be fine-tuned in order to raise our accuracy. First, we can collect more data, as we currently only have data for 200 cities, and we're looking to increase our data set by at least 200 to 300 more cities. Also, we can improve our data set by adjusting our feature selection, which means experimenting with adding different features like high school education rather than college, the distribution of different job types, or whether a city's population has increased or decreased in recent years, to name a few. And finally, we will test our data on different algorithms, including XGBoost and neural networks, to see if our model can achieve a higher accuracy score. When all this is complete, our model will have a stronger data set and will be used to predict crime rate for different cities in the US with even greater accuracy. So here is a chart of our current model's feature importances. So the scores on the right are generated based on the importance of each feature in our current model's prediction process. In the future, after we collect more data, we can use the importance score to give insight on which features we may consider removing or keeping in order to refine our dataset. So currently our top 5 features are median household income, the police count per 10,000 people, the percentage of Black population, the percentage of population with disabilities, and the percentage of white population. It's important to note that the more accurate our model is, the more trustworthy the feature importance scores are. So these scores and the order of importance may change upon further testing. Here are some other elements to consider while interpreting our model. When interpreting the model's feature importances, it is important to note that the generated feature importance only scores the correlation or statistical association between features and classification. And this correlation does not imply that any feature will cause our predicted classification. Also, the general cautioning for machine learning models applies here in that any unintentional bias in the data collected will be reflected in the model and may produce biased results. Furthermore, in real-world application of our model, there are limitations to our predictions since the historical data we use for prediction are from past years and may not reflect any current changes in society that may affect future crime rate. Now we have our sources. So these are the sites from which we got our data. And finally, we'd like to thank the ASDRP for providing us this opportunity and our advisor, Mr. Subramaniam, for all his help and guidance throughout this project. Thank you. Does anyone have any questions?
I have a very simple one to start with. What is a stress score? How do you measure stress?
Okay, so we got our stress score from a website which took in a bunch of factors such as average work time per day and average income, and they combined it all into a number.
So it's a computed number that comes from somewhere other than yourself.
Yeah, that's correct.
Okay. You got somebody with a hand up there.
Oh, Lucas, do you have a question? You can unmute.
Hello, thank you for the nice presentation. So I have a suggestion about your feature importances. So one of the things you can do with the sklearn package in Random Forest is you can pull out a different feature score for the different trees in the forest. And then that can give you some error bars that you can put around your feature scores, because you know, some of those features might be a little contentious, and it might be a good idea to try to put an estimate of an error bar on those. So you can see if they overlap or they're really if the third most important feature, is it really, you know, the third most, or is it equally important with the fourth most? So, and you can find information online about how to do that. So yeah, it would be a nice way to add some error bars to your estimates.
Thank you for the suggestion. We'll consider doing that.
Well, that's a pretty loud silence. I'll go on record and say thanks. Great presentation, guys.
You're done.
Yeah, good job, guys. Yeah, great
Okay.
presentation. Yeah, thank you.
Yeah, you're
All right, thank you. And our next group is going to be the autonomous vehicle group. Is Araja Ali, Sanjay, Karthik, or Siddh here, or Sunny?
Oh yeah, me and Ollie are going to present it.
Okay, let me give you a quick introduction. We have a group who are investigating how to build safe autonomous vehicles that are capable of safely driving on the road without running into each other or stalling out or doing something like that. I will let the group take it over from here.
All right, so I'll just share my screen. Okay, so all right, so the project that we're doing is deep reinforcement learning with autonomous vehicles. So we're trying to find a way to sort of make decision making with self-driving cars as accurate and as good as it can be. So there's been a lot of research conducted for autonomous systems. The use of autonomous vehicles has proven to be more efficient and effective than human control. And due to advancements in accessible processing power and lower costs in sensing and computing technologies, research in autonomous systems has advanced dramatically in recent years, culminating in a mature technological level of fully autonomous cars. So we've been seeing a lot of self-driving cars lately, and because there's more power for these cars to make more decisions, we've been seeing more technology related to these self-driving cars. So there's been more research and more technology with them. So deep reinforcement learning algorithms hold many opportunities for research in autonomous vehicles. So specifically when cars have to make decisions, deep reinforcement learning is a good solution to this. And prior research has been done on decision making, and we plan to sort of continue this research and see what's the best way, even within deep reinforcement learning, for these self-driving cars to make decisions. So we're going to be using robotics equipment from ASDRP and also from the VEX robotics competition. And we're going to do both hardware and software. And we're going to train our algorithm to get high accuracy results and then test it using hardware. So just first going on to like a background of deep reinforcement learning, it's basically a combination of deep learning and reinforcement learning. So deep learning is a form of machine learning that uses neural networks, and it's involved in handling complications and raw input data like pictures. And reinforcement learning basically uses trial and error, and the AI sort of learns to make decisions by trying things and then seeing what the result is. So within deep reinforcement learning, there are two types of algorithms, and one is model-based, which is supervised learning through a neural network, and then the other is model-free, where the policy is learned with technically modeling forward dynamics. And there's many different methods involved with deep reinforcement learning, such as exploration, off-policy reinforcement learning, inverse reinforcement learning, and goal condition reinforcement learning. So we're still trying to figure out some of the different methods specifically that self-driving cars use currently, and we're going to be exploring each of these and seeing which is sort of the best one within deep reinforcement learning. So deep reinforcement learning can specifically be applied to self-driving cars. So obviously with a self-driving car, since there's no human controlling it, there's no human making decisions, this means the car itself has to make decisions in all possible scenarios when it's on the road. So reinforcement learning is a potential solution for decision making within self-driving cars. So specifically to prevent collisions and just make decisions about speed and other things on the roads. It will use deep reinforcement learning. So the approach to this problem would be the car would sort of gather the environmental information and switches states based on a policy to maximize rewards. So this is based on a reward function. Basically, the car will try out different things and it will see where it gets like the biggest sort of reward. That's how the reward function works. And we will consider different aspects such as power consumption and safety. So next is on to the hardware, and Ollie's gonna do this part.
Yes. So next we want to talk about the outward structure and the hardware of the robot car that we'll be building. So the hardware we'll use. I try to make this easier to understand, so I divide it into 5 categories. Right now, we'll just look at what the parts are, and since not everyone here knows what each part exactly does, I'll also explain the specific uses later. First, we have the processors. We'll only have one main processor, and the specific model we'll use is Raspberry Pi 4 Model B. And the sort of code that we'll be uploading to this, which will be talked about later in the presentation, should work perfectly with this. Next, we have 2 controllers, a motor controller, also called an H-bridge, and a microcontroller. The specific microcontroller that we'll be using will be Elegoo Uno R3 board. Then we have a sensor for which we'll use a camera. We did consider LiDAR, but the group decided that a camera will be a more better option because it will be better able to collect data and provide more accurate results. Next, we have a chassis kit. A chassis kit is basically consisting of baseboards, wheels, and wheel motors, which essentially help keep the robot together. Lastly, we have other parts such as jumper wires, a power bank, and USB cables, which are important, but relatively less important. So we talked about what the parts are, but what are we using them for? So we can go through these together. A chassis kit, as already mentioned before, has baseboards and wheels, and it essentially just provides a physical structure for the car where the processors and the power sources can sit on and rest. Next, we have the processors. Now, the processor is a really important component of our project because it connects our deep reinforcement code to the physical car. This is the piece that connects the software to the hardware. So we'll be uploading our code to the processor, which will direct the physical car, which will help the robot function. Next, we have our two controllers. First, let's talk about the motor controller, or the H-bridge. Now, the H-bridge directly controls the wheel motors and directs the car on what speed and what direction to operate in. So it basically is in control of the steering wheel and the gas pedal. Next, how do we tell the H-bridge what speed or what direction we want the car to go in? Well, for that, we have the microcontroller. We direct the microcontroller, which in turn directs the H-bridge, which controls the wheel motors, which control the speed and the direction of the car. I think we already touched upon the cameras, which basically awares the car of its surroundings and helps collect external data. Lastly, I know we talked about these microcontrollers and main processors. Well, these need power to function, and we will provide that power by simply just using a power bank. Next slide, please. Here's some of the pictures of the most relevant parts of the robot so you guys can better understand and see what each of these look like and do. And next slide, please. And finally, when we're done building our car, it should look something like this, at least we hope. And then, so let's talk about the other work that's going on this subject. Unfortunately, the person most knowledgeable on this topic was not able to be here. So I'll only be able to provide you an overall picture of what's going on here, but I'll try my best. So now we did find another research paper on this subject, but the researchers only used a simulation called Torx and never actually tested the algorithm in real life. And as we know, there are many multiple confounding variables and factors that can interfere with real life situations. So our group plans on changing this and actually testing it out and seeing an autonomous vehicle controlled by deep learning and reinforcement for its real value.
Okay, so for further research, there's many possible further applications of our research. So since we're using deep reinforcement learning, we can of course apply different and a more variety of environments to fine-tune the car and improve its accuracy and the functionality, and overall just make sort of the accuracy and our current models even better. So these are our sources, and then we would like to acknowledge Dr. McMahan for assisting us throughout this project, as well as the Computer Science and Engineering Department at ASDRP for providing us with this opportunity.
Maybe you should wait and thank me after you find out if all your parts came in or not.
I think they did come in, so thank you.
Yeah, now we just have to figure out where I put them.
Does anyone have any questions?
No questions. Good job, though. Thank you. Looking forward to seeing this project go.
I have a question and a comment.
Yes, sir.
So my comment is, why is deep reinforcement learning the best kind of machine learning for this sort of a project?
I think I can answer that.
Okay.
It's when we were sort of doing like our literature review and trying to see what existing methods there were for decision making, deep reinforcement learning was typically the one I found the most done for this, but I think it's because of the way the reward function works. So it sort of puts a car through many different scenarios, and if, for example, a car would crash, then that's a bad thing. So a car would try to avoid that later on. So I think it just makes a lot of sense when it comes to self-driving cars. They will always try to avoid bad situations and prefer like situations where they get the most reward, which is like not crashing.
Okay, so I have one comment on the presentation style. What I will say is, don't read directly from the slide. The slide should be in outline format or shortened phrases, and you should be expanding on what's in the slide and talk to it without reading from it directly.
Yeah, thank you.
Okay, I'm through. Next person.
I've got my hand up. I've got a question. It's related to the question that was just posted in the chat. But so this looks like a very exciting project, and I'm questioning about the use of a single camera. With a single camera, it's hard to gauge distance. But if you have, say, a pair of cameras, you could do some triangulation or something to estimate a distance. If you had a LiDAR, you could directly also get distance. So do you think that might prove a challenge for the deep reinforcement learning algorithm to gauge the distance to an obstacle?
I think I can take this one, and I'll also answer the question in the chat. So for the people who don't know what a LiDAR is, it's a sensor that uses radiation to detect objects, while the camera, on the other hand, uses vision. And we thought our group had a possibility of stepping the project up and maybe making our autonomous vehicle road safe. And a LiDAR would not be a very good option there, because we would need to detect stop signs and traffic lights. So that would pose a problem, and I thought, and the group thought that using a camera would be a better option. And to address your question, Mr. Lucas, that could be a potential problem that we are looking at currently. And I think you posed a solution there too, which was using multiple cameras. So we would try that out as well. We are currently working on it, so we'll put it through simulations and look at how the results are coming up, and then change whatever needs to be changed based on that.
That sounds exciting. It sounds like a fun project. Thank you.
Thank you.
Let me jump in here. There's also a cost factor, and it's not necessarily that great, but they are going through me, and I'm being somewhat penurious with the components that we look at. So yeah, dual cameras for stereo vision and stereoptic resolution down the road, certainly. Right away, actually it wasn't asked for, so I'd have to think about it. But it's not that they haven't thought about it, it's that I'm kind of the gatekeeper.
Well, I think the deep learning algorithms they'll make some mistakes starting off and bump into things, but over time, they'll probably learn to gauge distance from a single camera. And it'll be interesting to see how much data is necessary before they get there.
Yep. Thanks for your contributions, by the way. Thank you. Well, good jobs all around. Give yourselves pats on the backs, all of you that presented. Good job.
Okay, I think we're finished.
I think so. So from me, good night, everyone.
Good night.